Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Model 029, Design Process and Flowcharting. Please join me in this engineering lecture series by subscribing to my YouTube channel at https://youtube.com/at Michael C. Like, share the lectures with your friends, your fellow students, and drop your comments in the comment section or reach out to me using my email addresses. As a prelude to this lecture, I will expect you, even after this lecture, to look up my lecture on general purpose computers. That is at Module 014, Part 5. Computer software types at Module 014, Part 4. And components of computer system on Module 014, Part 2, using the links stated. As we go on in this lecture, I will be intermittently giving what I call self-test. That is to help you know how far you are following in both this lecture and the previous ones. And I expect you to answer those self-test questions in the comment section so that I will be able to see them and correct you if you didn't get it. And mind you, as you answer the self-test questions, you will be accumulating some points for yourself. Now, let's go. Design procedure. The key to process design using computer is to break up the problem which the process is desired to solve into small pieces rather than approaching it as a whole. Each of these small pieces can then be viewed as single step in the overall step-by-step process of the design. Now, the step-by-step process includes 1, problem identification. And we say, as in many situations in life, the first step is the clear understanding and identification of the problem. Incorrect identification will either incorrectly solve the problem at hand or solve the wrong problem. So you must identify precisely and concisely the problem you want to solve. The problem identification step must also include identification of the data to be used in the system and the desired result, that is the output you are expecting from your design. Usually, the program is completed. When the program is completed, one returns to this problem identification stage to ensure that the problem solved is indeed the identified problem. Step 2, since computer can follow only specific instructions to perform an operation, the next step, that is step 2, is to develop a step-by-step solution for the problem at hand. This step-by-step solution method is termed an algorithm, which must correspond to the logic of the program. Step 3 is a conversion of algorithm. In step 2, we talked of developing algorithm is the logical step to solve the problem. So this step 3 is the conversion of the algorithm to an acceptable form for the computer before preparing the actual program. Once you have an algorithm, you are well on the way to performing the desired task. However, we need to go one step further to ensure the program we write will actually represent the algorithm we have developed in step 2. This conversion can take either of the two forms, one written and the other pictorial. The written form is referred to as a pseudocode, and the pictorial form is referred to as flowcharts. If you see, our topic is design and flowcharting. So we will get in more details to see what flowcharting is. The conversion of an algorithm to pseudocode involves actually writing program in the programmer's language rather than a computer language. For us, we write in English. A pseudocode is necessary for two reasons. One, it simplifies the logic in the algorithm, and two, it provides a relatively direct link between algorithm and the computer program. Example of a pseudocode is, if you look at it, you think that it's a program, but it's a pseudocode. Say, if x greater than y, then output x, else output y. This is not any computer language programming, but it looks like you understand what is expected to be done. You're comparing two numbers, x and y. If x is greater, then you output x. Else, if y is greater, you output y. It can go further to be a more lengthy description. Example 2, begin program. You want to start. Then input name, registration number, and 3 scores. You have not written a program, but you will use it to know what to do next. Set total to be equal to score 1 plus score 2 plus score 3. Set your average to be total divided by 3. So if average is less than 60, then output message that student is failing. Then end of if block. We will see as we go on. The minute you use if, then you must specify when the if condition will end. Then output name, range number, and average. So you put the name of the student, his range number, and the average score. End of program. So you see, this is a pseudocode. If you look at it, it looks as if you have written a code, but not in the real sense. So step 4, so call it program preparation. This step is the statement by statement conversion from the pseudocode to whatever language that is being used to program the computer. Step 5 is the conversion of the coded program, and we say that after the conversion of the pseudocode to the language being used by the program or the programmer to program the computer, the program will be put in the form readable by the computer. The most common ways of doing this are: you can feed it in through Bluetooth, you can feed it in through interactive input, through your keyboard, you can feed it in by any other device or drive and so on and so forth. So at this point, we take our first self-test, and that self-test is: name other input devices you know. And we say you can check them out in Module 14 or 014 Part 1 to 7 of this engineering lecture series. You will see where we listed all the available inputs you can use, or input devices you can use to input commands or anything to your computer. So step 6 is the compilation of the program. Most programming languages are what we call the high-level languages that must be translated to low-level machine language before the computer can understand the program. Also, in the past, we've looked at the high-level languages, and we say that these are programming languages that resemble the human language, but the computer will be able to translate it to its own low-level machine language. And when we talked of machine languages, we talked of, machines understanding zeros and ones. So our self-test number 2 is: can you name 2 examples of high-level languages and low-level machine language in the comment section? We go on. This translation stage is known as compilation and occurs after program statements are keyed into the computer along with any necessary job instructions and data for the program. And quickly, our self-test 3 is: what is the work of the compilers? If you get also to the models we reference, you'll be able to get that. Then step 7 is the execution of the program and debugging. After the coded program has been compiled, it is run to ascertain the efficacy of the program. When we say that you are running a program, it's just like, testing or making the program to do what you want it to do to see if it is error-free. When you do that, you say that you have run the program, or you are running the program, or that the program is being run. Any of the sentence can stand. If errors occur in the execution stage, it is usually found and corrected. In this stage, errors can be syntax error or logical error. By syntax error, we mean, depending on the software you are using, even when you put a comma where it is not supposed to be, will signal an error. And that type of error is called syntax error. The process of tracking down the execution errors and correcting them is referred to as the debugging process. And when a program finally runs error-free, it is said to be debugged. So when you run the program and sort out where comma is supposed to be or is not supposed to be, and it is there, and where you are supposed to click your enter and you didn't do that, you find them out and correct them. When you are doing that, you are debugging. You are removing the bugs in the program. And when you finish that and your program is error-free, then it is said that your program has been debugged. So we look at our self-test 4, and that self-test 4 is, what do you understand by debuggers? Step 8, which is program use with actual data. So after the program has been compiled, it is usually executed using test data. Our last test for tonight is, can you name one program compiler software you know? Then the actual data is used to further run the program, and the final result is analyzed to determine whether the result meets the objectives outlined in the program identification step. If the final result did not solve the identified problem, then the whole steps from step 2 to step 8 will be repeated, because it means that you have not been able to solve the identified problem. Then, if you go back, you repeat the steps until you are able to solve the identified problem. And in now really implementing, you have to develop what we call the algorithm. To say the majority of processing tasks that computers are expected to perform are not always formulaic problems. What do we mean by that? If you look at an example, you want to find the profit in anything. You have to get the sales minus your expenses, and in some cases the tax. Whatever that is remaining for you is your profit. So this is a formulaic problem where you can put in the formulas to get your answer. But in real life, not all programming process will follow these formulaic problems. So we say, although many processing tasks contain subtasks that can be solved by formulaic approaches, additional processor capabilities are required, including the ability to compare data items and to alter the sequence of instruction execution, such as branching. We have made branching in our previous lecture when we talked of the addressing techniques. So when you encounter such things, you see you are not solving formulaic problems, but you are trying to alter the sequence of execution of the program. So say that programming languages implement this capability with an if then or if then else. It's not always if this then this. But at times you can have if this, then that, else that. So a problem-solving procedure or program that uses comparison and branching functions is usually called an algorithm. Therefore, an algorithm is any procedure that specifies a finite set of steps which, if followed, gives a solution to a problem. So, part of our main work today is flow charting. You see, in anything you do, even when you get to the point of carrying out your projects at undergraduate level, at postgraduate level, even when you engage in real life, it's always good for you to know how to prepare a flow chart to show how you start from a place and get to the end with all the possible decisions that will be taken. So, flow charting is very important in your life as a student, as a graduate, as a working class person, as a researcher also. So, an important tool, and that is why we call it a tool. Flowcharts is a tool. An important tool for writing a program is the flowchart. It enables the programmer to plan the sequence of operations in a program before writing it. Flowcharting, therefore, is a convenient way of expressing on paper in diagrammatic form the activity